You are watching the Control Design educational video series, Get a Feel for a Machine's Position with Sensors. This video is brought to you by our sponsors, MTS Sesnrors and Balluff. More information on our sponsors will be provided later on. You can also find company and product information provided in the information section below. Our presenter today is Control Design Technical Editor, Dave Perkun.
While industrial controllers and cylinders provide the brains and muscle for automated machines, the sensors add awareness, precise control, optimized performance, and quality. The automated machines of today and tomorrow demand it. The discrete position detection devices, such as photo eye, inductive, and capacitive sensor, and encoders, and linear position sensors for more advanced motion applications, provide required machine control feedback functions. While added cost, installation time, programming requirements, difficulty adjusting, and maintenance may lead a designer to eliminate sensors, in many applications, the need for a sensor is obvious. However, some may argue that it is not necessary to sense every position, or the sensors can cause more problems and related downtime than they're worth. When airproofing manufacturing is added to the discussion, the addition of sensors is best practice. End of travel, part presence, and full stroke sensors become a requirement, and their application as well as the connection method and data they provide should be carefully considered. Airproofing includes sensors and data. A discussion of part presence cannot be complete without including cylinder or actuator position sensing. In most cases, position sensors on cylinders and actuators are considered a best practice for automated equipment. The position sensors provide real feedback for use in the program logic, incrementing the sequence only when a cylinder reaches a position. And while these sensors detect end of stroke, they should never be used as hard stops. An alternative to position sensors is to use timers. When done, the program logic assumes the cylinder has reached a position. Timers are a poor choice, and a program that uses them is just hopeful logic, hoping that the air pressure is okay, the flow control hasn't changed, and the cylinder is moving at a constant speed is not a robust automation plan. A lazy cylinder can cause problems. This timer-based method can also slow down the machine while waiting for timers to time out. The bottom line for the use of presence and position sensors is the need for airproofing and improving quality. Logic decisions based on actual position, not time delays, and detection of the part presence, not assuming it is there, makes better parts faster. Sensors improve final product quality. Sensing part presence and completed assembly are just two of the quality checks sensors can provide. A lack of sensors may save money, installation time, and programming, but how do you know you are making a good part or a proper assembly with all the parts present? You need to sense it. And while you're at it, add a reject part offload sensor to make sure failed components are accurately controlled and dropped in a reject bin. When in doubt, add a sensor. It's often the best option to airproof the machine to make better quality parts. Beyond presence sensing, there are many paths to follow for linear position sensors in machine automation, including a rotary resolver or encoder, or an optical, magnetic, inductive, or magnostrictive linear encoder. Some of the basics in selecting a linear position sensor revolve around response time, resolution, and accuracy, all of which are driven by the application. Rotary encoders may win the popularity contest and provide higher resolution solutions, but the resolver or linear encoder has much overlap in application, and their designs often make them more robust options. Certainly the device must work within the intended environment and connect to the controller. When it comes to sensors and feedback devices, they must handle the environment where installed. Sensors need to be tough enough, and most are, but encoders are often fragile and unsealed. Clearly, some are meant to be embedded and protected deep inside a motor end cap or an enclosed kiosk due to their plastic housing, ribbon cable connection, and open design. A sealed metal housing with circular connectors is a much better option for the plant floor. A common discussion about position sensors revolves around specifications. How many pulses per revolution? What type of output? Incremental or absolute? These questions must be answered. However, there are often many considerations when deciding to use them on a machine. These devices must work to get better control of a machine position, but they also must work well in the control system. An encoder's purpose is to report the position of a linear or rotary motion as a digital signal to a controller, which then uses it for monitoring and control purposes in a variety of machine tools, multi-axis positioning systems, and robotics. With a little math programming or built-in controller functionality, this digitally translated position can be used to monitor velocity, distance, angle, acceleration, deceleration, and direction. The technology in linear position sensors enables users to develop higher quality machines that are more efficient. Designers can take advantage of sensor capabilities, such as addressing the needs of the Industrial Internet of Things, IIoT, and Industry 4.0. Industrial Ethernet and IO-Link drive seamless integration of these smart sensors, adding to the data and information available, which aids functional understanding and control of a machine. With the IIoT, the challenge is determining which information is most valuable and deciding on the best way to provide this information to the user. If you're going to connect the sensor, it must provide actionable information for rapid troubleshooting to minimize downtime, schedule maintenance, and predict future failures. In addition to analog and pulse and direction signals, there are many industrial Ethernet options available to make the connection to linear position sensors to provide more information. Another solution to IIoT connectivity is IO-Link. It works with most fieldbus and industrial Ethernet networks by using an IO-Link master that becomes a remote I/O node. IO-Link communication provides the ability to remotely monitor sensor performance and health, establish alarms, and even predict when maintenance will be needed based on real-time sensor data. With this information, sensors can be replaced during scheduled maintenance, avoiding unnecessary downtime. Most IO-Link devices and sensors can identify and configure themselves. It's a simple plug-and-play, standard, unshielded 3-wire connection to a sensor. Once connected, it allows monitoring of devices and continuous diagnostics, data logging, and error detection. It makes it easy to configure sensors and provides diagnostic information on issues such as broken wires and communication failures.
Thank you for watching Get a Feel for a Machine's Position with Sensors. This video has been brought to you by our sponsors, MTS Sesnrors and Balluff. MTS Sensors capabilities include Ethernet and IP with CIP sync and DLR, position and velocity measurement for up to 20 magnets, and field adjustment and diagnostic using the new TempoLink Smart Assistant. The Balluff Machine Vision, simple to set up, easy to operate, with flexible camera options, standardized industrial network interfaces such as Ethernet IP, Profinet, and TCP/UDP, and no software install. Use any web browser to access the BVS cockpit.